Welcome to part 2 of the lecture on data flow analysis. So, data flow analysis derives information from the data along the program execution paths. So, in general there is an infinite number of paths through a program and there is no bound on the length of a path. So, program analysis actually summarize all possible program states that can occur at a point in the program with a finite set of facts. So, and there is no analysis which is a perfect representation of the state. So, we saw in the last lecture the reaching definitions problem, and quickly to recapitulate the reaching definitions, if a definition reaches a particular point, then it implies that from the point of definition to the point at which we are considering, there are no more redefinitions to the variable involved in the definition. So, these are the data flow equations. There are two quantities gen and kill here. Gen is the set of all definitions. This is the local reaching definitions, set of all definitions inside B that are visible immediately after the block. These are downward exposed definitions, and kill B is the union of the definitions in all the other basic blocks of the flow graph that are killed by the individual statements in B. So, the inset is a union of the outsets of the predecessors of the basic block. So, this union is the confluence operator in this data flow problem, and the outset is a union of the gen set and then whatever is coming from the top in B, and remove kill B from it and union into gen. So, that is what gives you out B. In B is phi for all B as an initialization. So, here is the example that we considered in the last lecture. So, there are 7 definitions here and 4 basic blocks. So, here are the gen and kill sets, and initialization of in B1 is phi for all of them. So, out B1 trivially will be gen B1 itself, because in B1 is phi. So, then after one pass the values become as shown here, and the final set of values is in this fashion. So, if you take for example B4, what is generated is D7, it is always so, and what is killed by B4 is D1 and D4, because these are the two definitions of I which appear outside in the basic blocks. In B4 is D3, D4, D5, D6. So, D3, D4, D5 and D6 are the only definitions which reach this point. D1 and D2 do not, because when they try passing through B2, they are killed by these two definitions. Now, how do we implement such a data flow analysis, let us say for reaching definitions? This is actually a fairly straightforward implementation. So, there is this thing a while loop which keeps looping until none of the sets outsets in the system change. So, how do we do that? The initialization is of course in B equal to phi, and out B is gen B. It could have been phi as well, but gen B reduces the number of iterations. There is a Boolean variable change. So, while change do. So, to begin with, we set the change as false, assuming that we need to iterate once more. Compute in B as given in the equations. So, union of the outsets of the predecessors. Then old out is retained as out B, and out B is recomputed as gen B union in B minus kill B. So, if out B is not the same as old out, then change is set as true. So, we keep going. Okay. So, if change is true, then we go back and do it once more. If change is false, we then get out. So, gen, kill and in and out are all these are L sets, they are represented as bit vectors with 1 bit for each definition in the flow graph, and here is an example to show how it can be done. So, I have shown this only for the basic block B 1, but it is going to be similar. So, there are 7 definitions in this program. So, there is 1 bit for each definition. So, we have 7 bits necessary to represent this data flow information. So, each one of these gen, kill, in and out are sets. So, we are representing it as a bit vector. So, for example, if you look at the previous this thing here, gen B 1 is D 1, D 2, D 3 and kill B 1 is D 4, D 5, D 6, D 7. So, D 1, D 2, D 3 implies we set ones in the 3 positions corresponding to D 1, D 2, D 3 and then the rest are all zeros. So, D 4, D 5, D 6, D 7 are the other definitions. So, we set ones in all these and zeros in these. So, this is a very simple representation for data flow sets or values. The advantage of this representation is that when we want to do a union or intersection or difference operation, for example, here we want to do a union operation here and we want to do a difference operation here. In later cases we may want to do an intersection operation as well. So, this union operation simply becomes a bit vector OR operation, and the difference operation can be similarly implemented in terms of the and OR operations. Intersection simply becomes an AND operation. So, the analysis the program to implement the analysis, reaching definitions analysis will be very fast because of these bit vector operations, provided there is a bit of caution necessary here. The entire set of these the entire set, that is the bit vector of data flow values, actually can be fitted into, should be fittable into a single word of the machine. It could be, if it is a 32 bit machine, then we can have a maximum of 32 definitions, and if it is a 64 bit machine, then we can have a maximum of 64 definitions fitting into a single word as bits. So, in that case a simple AND OR operation is possible, but suppose we have 150 definitions in a program, then no machine really has 150 or more bits in one single word. So, we may have to use multiple words to implement the bit vectors, and then we have to keep track of the positions of these bit vector parts as well. So, part 1, part 2, part 3, part 4, etc. So, and do the AND OR operations appropriately on all the parts rather than just one word as we see here. So, doing this definitely requires a little more work than just on one word. So, the efficiency goes down a little bit, but there may be no other option as well. So, this is about the reaching definitions problem. Now, we look at a variation of the reaching definitions problem to compute what are known as use definition chains, UD chains as they are called. In fact, UD information is nothing but reaching definition information. It is just that it is a very convenient data structure to represent such information. So, what is a UD chain? It is actually a list of a use of a variable and all the definitions that reach particular use. So, for each use in the program, we are going to attach the definitions that reach that particular use. So, let me show you an example quickly. So, taking the same previous example, there are all the gen sets and kill sets and in sets and out sets here. So, let us consider I comma D 4 as a use. The notation says you take the I, which is a use, in the definition D 4. So, that is our use here, and the definitions which reach this particular use, it is very clear. D 1 reaches it and then D 7 also reaches it. So, the UD chain for this use will consist of these two definitions D1 and D7. J comma D5 is the next use that I have considered. So, here this is the J and this is the D5. So, here D2 of course reaches it, and then this D5 itself is assigned after the use is completed. So, this D5 goes all the way, takes the back edge and comes to the top of this particular basic block and then reaches this use. So, both D2 and D5 use are reachable to this point, this use, whereas the same is not true for D4, because this D7 kills this D4. So, it is not possible for this D4 to travel all the way up to this point again. Okay. That is the reason why we have just a D1 and then the D7. A comma D7 is here. Okay. This is the usage of A comma D7, and here we have this of course D3, which can travel all the way up to this use like in this path, and D6 which can directly travel along this path. So, these are the two definitions which reach this particular use, and finally, J comma D7 is in the same instruction D7. So, the only definition which reaches it is D5, that is this particular J. This J will not reach this use, because when it tries to pass through this basic block, this D5 will kill D2. Okay. So, it is not possible for us to get that D2 into this place. So, let us see how to compute such a data structure. So, UD chains may be constructed using constructed once the reaching definitions are computed. There are 3 cases. Let me show you a picture which corresponds to these 3 cases, and then we will read through the information given here. So, here are the 3 cases. The first case says there is a basic block B, then the inset, that is the reaching definitions coming into this basic block have been already computed. There is a use of the variable B, let us say this is called use U1, and then in the rest of this basic block there are no unambiguous definitions of B. So, recall that unambiguous definition implies direct definition using a variable, that is something like B equal to, and not through a pointer, star P equal to, where P may point to the variable B is considered as ambiguous. So, we have no unambiguous definitions here, no direct definitions B equal to in this part. So, if that is so, the only definitions which can actually come into this basic block are through the set in. That is why attach the definition of B in the inset. So, there may be many of them here, definitions of B, whatever are in this particular inset are attached to the UD chain of the use U1. So, these things they all reach here, because there are no other definitions to kill the older definitions. So, this is one case, and we can demonstrate this case very simply here. Let us take I D4. So, D4 is here, I is here. So, now in this block there are no other definitions of I before this is used here. So, we look at the inset, and in this inset the definitions of I which correspond which definitions which correspond to I are D1 and D7 only, right. So, D1 and D7 are the ones which correspond to I, and both are attached to this particular use. The second case is, again there is a basic block, and we are looking at the inside of a basic block here. So, here is a use U1 of the variable V, and then here is a definition D1 of the variable B, and in the middle there are no other definitions of the variable B, and again we are considered only with unambiguous definitions, and we are not considering ambiguous definitions because we do not have to deal with them. they do not kill any other ambiguous definitions, do not kill any definitions, that is why we do not have to deal with them. So, for this definition can straight away reach this use, the value here is what is valid here. So, therefore, we can simply attach the definition D1 to the use U1 and put it on its UD chain. So, this is the second case. Remember that if there were any other definitions which reach through in V, like here, they will all be killed by this. Okay. So, none of them need to be considered, only this definition needs to be considered, and that is why attach definition D1 alone to use U1. The third case is again basic block B. There is a use U1 here, there is a def D1 here, B equal to, and in between there is star P equal to, which is ambiguous definition of B, that is, let us call this as D2. So, what happens now? Here there were no unambiguous definitions, here also there are no unambiguous definitions, but there is one ambiguous definition. If that is so, you see P star P equal to is ambiguous. So, P may be pointing to B at the time of execution of this basic block, or P may not be pointing to B at the time of execution of this block. So, we are conservative. So, we will assume that both the definition D1, that is this one, and the definition D2 are attached to the use U1. So, this is the conservative nature. There are two of them which are made to actually reach this B. Well, obviously, if P is pointing to B at runtime, then this definition will not reach this point, and if P is not pointing to B at runtime, this definition will not match, D2 will not reach, but D1 will definitely reach. So, either one of them will reach, and since we do not know which one of them is going to reach, we will say both of them reach. So, that is what I have said here. Case 1, if you use U1 of a variable B in block B is preceded by no unambiguous definition of B, then attach all definitions of B in the set in B to the UD chain of that use in U1 of B. So, this is very similar. There are, if any unambiguous definition B precedes a use of B, then only that definition is on the UD chain of that use of B. And case 3 corresponds to the ambiguous definition that we saw, they both of them are attached to the use of B. So, we already saw this particular example. So, let us proceed further. Let us take up the second data flow computation problem. This is known as the available expression computation, and this problem is essential to handle the common sub-expression elimination optimization. This is also a forward flow problem, but the confluence operator here is intersection. What is meant by availability? So, let us define that. It is very simple. An expression x plus y is available at a point P if every path, not necessarily cycle free, from the initial node to the point P evaluates x plus y. So, this is very important, and after last such evaluation, prior to reaching P, there are no subsequent assignments to x or y. So, this is something I want to show you here. So, let us consider the expression 4 star j here, there is another 4 star j here. This is the same example that I gave you during introduction to optimizations lecture, and there is another 4 star j here. We have marked 4 star j by red arrows here. So, this 4 star j is said to be available at the entry of the basic block B6. So, how is that? When we say 4 star j is available here, we are supposed to look at all the paths from the initial node to this particular point and make sure that there is a computation of 4 star j. Well, let us trivially made sure of, because every path that reaches here goes through this basic block. There is no way you can actually reach this point otherwise. So, once we go through this basic block, 4 star j is computed, and we are not assigning any value to j here, j actually gets assigned only here. So, j definitely 4 star j definitely reaches is available at this point. Similarly, j plus 1. So, j plus 1 is used here and here. So, if we want to make sure that j plus 1 is available at this point, we must make sure that it is computed along all paths to this point, and j is not redefined again, which is obviously true, because again as I said, every path that comes here will go through this basic block. Suppose you look at I minus 1, I minus 1 is here and I minus 1 is here as well. And we want to make sure that every let us look at availability of I minus 1 at this point. We want to make sure, starting from the initial node, when before reaching this particular point, the beginning of B8, I minus 1 is evaluated and then I is not redefined. So, we go through this, right. So, we evaluate I minus 1 and then we can directly reach this, that is one path possible, and definitely I minus 1 is evaluated and it is not, I is not redefined. So, we may actually go through this entire thing, we go through this particular loop, go out, come back again, go to the same block B4 and then travel to this point. So, if we do this, we still see that I minus 1 is evaluated here on this way, but it is not I is not redefined anywhere else. The third path of course is it comes out like this, goes through this, then takes this true exit, goes out and then enters B4 and finally enters B8. Again this path also does not have any redefinition of I, and I minus 1 is evaluated here. So, I minus 1 is definitely available at this point. So, this is the meaning of availability, which we demonstrated that this cycle free is not essential, we went through the cycle also. What about generation and killing of expressions? So, there is now a pattern in these data flow schemas, right. We must identify whether it is a forward flow or backward flow problem. We must identify the confluence operator, we must write the constraints and we must write gen and kill sets. So, what about killing? A block is said to kill an expression x plus y if it assigns or may assign, both are okay, to x or y and does not subsequently recompute x plus y. So, here unlike in the case of reaching definitions, the kill part is conservative when it says even may assign is good enough for me to kill. So, I evaluate I assign a value to either x or y, either directly as x equal to or y equal to, or through a pointer star p equal to, where p points to either x or y. So, even this is taken as an assignment to x or y. Okay. So, if there is an assignment, then the previous value of x plus y does not hold anymore. So, this assignment is said to kill this expression. So, that block kills this x plus y, and of course, there should be no subsequent recomputation of x plus y. Let me make this very clear here. So, here is T1 equal to 4 star I, which is in the block B1. Then along this path there is no more redefinition of I. So, 4 star I travels along this path to this point. But what about the other path? There are two possibilities. One is there is no assignment to I. So, then we take this solid arrow and go to this block. So, if there is no assignment to I cannot be modified. So, 4 star I becomes available along this path also. If we consider the other option, there is an assignment to I, but then there is a recomputation of 4 star I. So, even in this case, even though I is modified and this value of 4 star I is this expression 4 star I is not valid anymore after this, we recompute 4 star I and 4 star I is said to be available at this point. Please remember that we are not looking at the value of the expression, we are only considering the expression itself. So, here is 4 star I, here is 4 star I, this may actually have a different value of I compared to this. There is a redefinition of I here. So, this 4 star I may be different and this 4 star I may be different, but when we do common subexpression elimination to eliminate this 4 star I, we simply put this 4 star I into the same variable, say some temp equal to 4 star I and say T2 equal to temp here. Here also it will be temp equal to 4 star I. So, we are not really worried about the actual value of I or the expression, but it is just that the evaluation of 4 star I is carried out along all paths, and we do not have to do it more than once if we perform the global common subexpression elimination. What about the generation of x plus y? So, a block generates x plus y if it definitely evaluates x plus y and then subsequently does not redefine either x or y. This is very easy to check here. Let us look at the example. So, here is a small block. Does this block generate I minus 1? Definitely it does, because it is evaluating I minus 1, and after this there are no more definitions of I. What about this block? The same, this block does not generate I minus 1, because T2 when I minus 1 is evaluated, but I is redefined here. So, at the end of the block we cannot get this value of I minus 1, I has changed. So, I minus 1 might have changed. So, this is what what about 4 star j here? 4 star j is evaluated here, and in the entire block there are no other definitions of j. So, at the end of this block, this gen set for this block will definitely contain 4 star j. This block will also contain 4 star j, because at this until this point we have not redefined j. So, that is about generation and killing, and we already saw this example. Now, let us look at the data flow equations. The equations again have there are 4 of them, rather 2 of them, in B and out B, and the other 2 equations are really initializations. In of B1 is phi permanently, it is not going to change. Why? The B1 is actually an initial or entry block and is special, because nothing is available when the program begins execution. So, that is why in of B1 no expressions are available on entry to the basic block B1. So, this is phi. And for the other blocks, in of B is made as u, where u is the universal set of all the expressions in the program. So, we are considering one procedure as a program here, and B not equal to B1. For B1, phi is the final value. Why should in of B be u, and why should it not be initialized to phi? So, we will see that u is always better than phi with the help of an example a little later. And why is this the confluence operator intersection? That is because this equation has intersection of out P, where P is a predecessor of B. So, this is the confluence operator intersection. And why is this a forward flow problem? This equation has out B and in B. Out B is being computed in terms of in B. I already mentioned that E gen and E kill are constants. They do not vary as the program executes. So, that is why this is a function of in B. So, a forward flow problem always has out B as a function of in B. Let us understand why this is correct. So, if you are looking at in B, it is an intersection of all the out P sets, P is a predecessor. So, let us look at an example here. So, for example, when we look at a particular basic block, let us take this. Okay. Let us take this basic block. Here there is one incoming edge here and another incoming edge here. We want to compute the in B of a basic block. So, let us say we want to compute the in of this particular basic block B 7. Then we take the intersection of the outset of this particular basic block and the outset of this particular basic block y. So, and then take the intersection, of course. Why should it be intersection? The intuition is, suppose there is an expression which reaches along this path, right. So, we start here, it gets evaluated and then it reaches this particular point. Now, there are a couple of expressions which may reach this point like this along this path. Similarly, there are a couple of expressions which go through this path and then reach this point. Which are the expressions which definitely reach this particular point? They are nothing but the expressions which are coming along this path and also this path, that is nothing but the intersection set. So, like in the case of reaching definitions, we do not take union because we want to make certain that the same expression comes along both the paths. Our requirement of the common subexpression elimination tells us that the expression should be reaching along all the paths and not just along one path. So, that is the reason why the data flow analysis schema, the equation has intersection. If the application is such that an expression is available if it reaches along any of the paths coming into the basic block, then this would have also been a union. But our CSE problem requires that the expression be available along all paths and therefore, it is an intersection. What about this? So, whatever is generated in the block and then union it with whatever is coming from the top of the block, that is the in B, and remove what is killed by the block. So, that is E kill. So, this is as in the case of reaching definitions, what something is generated, something is given to us, but something is being taken away. So, this is as simple as it can be. Now, we also have to look at some details of how to compute E gen and E kill. So, let us say the statement is of the form x equal to y plus z. Okay. Here we are at this point q and then we are given the E gen at this point q. Now, we are looking at E gen computation within the basic block. So, we have to look at every statement in the basic block, see how the E gen set is computed. So, to begin with at this point let us say E gen is given to us. If it is the beginning of a basic block, then this quantity A would be phi nothing. And now, there is an assignment x equal to y plus z. So, that means we are evaluating y plus z. So, this set A now becomes A union y plus z, because y plus z is being computed here. But then we are also assigning to x. So, all the expressions which had x like x plus k, x plus y etcetera are all killed by this particular definition of value of y plus z to x. So, from A you remove all the expressions involving x. Okay. So, that gives us the E gen set at this point. So, this is what the modification is for this particular statement. This is how we compute E gen. So, what we really do is we take the statements one at a time, start with the E gen equal to phi for the just before the first statement in the basic block, and for example, here if you are computing E gen for this basic block, E gen will be phi at this point, and then forget j equal to 0 for the present, because there is only a constant here. T2 equal to I minus 1. So, I minus 1 is computed. So, it is put into the T-gen set, and then T2 is a temporary. So, all the expressions involving T2 are removed from the E-gen set, in this case none. So, E-gen at this point after this statement will be just I minus 1. How about the kill set? It is exactly the other way. Whenever you actually compute an expression y plus z, it becomes available. So, we are going to remove it from E kill. It is not killed anymore, it is now available. So, A equal to A minus y plus z, and you have x equal to y plus z. So, x is going to kill a lot of expressions involving x. So, they are all added to the kill set, A equal to A union all expressions involving x, and that is our kill set here. Okay. So, to demonstrate this on this example, so we have j equal to 0 here. So, to begin with, suppose the kill set is u, all the expressions. So, this particular to begin with it is 5. So, now we involve all the possible expressions in the program which have j. So, for example, this 4 star j, j plus 1, these are the two expressions which we have. So, both these are put into the kill set here, and then we have T2 equal to I minus 1. So, I minus 1 is now available. So, it is removed from the kill set of this basic block, and T2 equal to actually obviously kills all the expressions involving T2. So, they are all added to this particular E kill. So, the expressions involving T2 are actually very few. So, it is only used here j less than T2 and so on. There are no other expressions involving T2. So, that is the computation of gen and kill, and we already saw the equations. So, now let us look at what happened after the available expression computation in this particular example. So, since I minus 1 was available at this point, we could simply take this particular T2 and replace I minus 1 by T2. So, that is the common sub expression elimination that we did here. Similarly, we have 4 star j in T4 here. So, it is also the same 4 star j that is here. So, we can simply say replace this 4 star j and this 4 star j by T4. So, that we did here. The same is true for j plus 1. So, T6 equal to j plus 1. So, we have replaced the j plus 1 at these points by T6. Okay. So, this is the GCSE that we did after the available expression computation itself. How do you implement this available expression computation? So, as usual the data flow analysis requires a while loop. It is very similar to the loop that we saw before, and the initialization is slightly different. So, for each block b not equal to b1, out b equal to u minus e kill. So, we could also have done in b equal to u. So, though no problem as such, and if we had done this, then these two should have been computed in a different order. The reason is if you know out b, then you can compute the intersection, whereas if you know in b, then you will have to compute out b first. That is the reason why the interchange is necessary. Otherwise, the final results will all be the same. Now, change is set to true and while change do. So, first of all make change false, saying that there is no change in any of the values. So, we may get out hopefully. In b is computed from the equation as intersection of out b. We store the old out value as out b, and out b is computed fresh as e gen union in b minus e kill. Now, if the new value of out b is not the same as the old value of out b, then we set change equal to true. It was set for false here. So, we iterate once more. Once the out sets have all stabilized, in sets would have automatically stabilized. So, we get out, and those are our stable values of in and out. So, that is how we this, and again I must mention here how exactly the implementation of the bit vectors happens. It is very easy to see that an expression cannot get into a bit, right. We said D1, D2, D3, D4 etcetera were all definitions. So, each one of these was given a bit. So, if there is a definition in a set, then that bit was set to 1. If the definition is not in a particular set, then the bit was set to 0. Here also we would like to do that for each expression. If there are 20 expressions, then we want to assign 1 bit to each of these expressions, and then say if that expression is in the set, then the bit is set to 1, otherwise set to 0 etcetera. But how do we assign unique bit numbers? There we just numbered took the quadruple number of the definitions. So, remember here, for example, let us look at this. Okay. So, we have numbered the quadruples D1, D2, D3, D4, D5, D6, D7. So, these are the bit positions we have assumed. So, whereas in the case of available expression computation, there is no number given to any of these expressions. It is possible that the same expression is evaluated many times. So, a unique number cannot be provided using the quadruple numbers. So, we use a hash table. So, what we do is the first time we meet an expression, we actually put it into a hash table. We hash the expression, go to that particular index and use that index value as the bit number. If the same expression is met again and again, we know the same bit number can be used again and again. Suppose the hashing has this problem of collision. So, more than one expression can hash to the same location. So, if the hashing function gives you the same location for a different function, then we use one of the collision resolution methods, maybe linear collision, quadratic collision resolution etcetera. Get a new index for that particular expression and use that index as the bit position for that expression. So, somehow using hashing we must map an expression to a bit position, and that makes sure that we can use the same bit vector operations of here we have intersection, here we have set difference, and we also have the union. So, these can be implemented very efficiently, and remember that the bit position is the index of the hash table. So, by going back to the hash table, we can also retrieve the actual expression itself. Then in the available expression, one small point was left out. We actually wanted to we initialized in B to the universal set, remember. So, we could do in B equal to u or out B equal to u minus kill. So, why are we doing this? We must demonstrate that initializing in B to the universal set is much better than initializing in B to phi. Okay. So, to do that, let us give an example. Take a very small flow graph B1, B2, B2 has a self loop. Let E gen B2 be G. So, E gen of B2 is G, E kill of B2 is K. Now, let us take how to compute the in of B2. You take the intersection of the two sets, out B1 intersection out B2. So, out B2 is again from the equation E gen, that is G, right, union in B2 minus K. So, out B2 is E gen union in B2 minus whatever is killed by this, that is K, E kill is B2 is K. So, now let us look at the various iterations of this loop. In 0 of B2 let us say is phi. We initialized all the ins to phi instead of u. Now, out 1 of B 2 in this case, because in B 2 is phi, nothing can be taken out of it, and out B 2 becomes g. Let us look at the second iteration. In 1 of B 2 is out B 1 intersection out B 2. So, out B 2 is g. So, out B 1 intersection g. What about out 2 of B 2, second iteration of B 2? This is again g union, this is in V 2, right. So, that is out B 1 intersection g is in V 2 minus k. So, the same equation in B 2 minus k, we have replaced in B 2 by out B 1 intersection g, and here is k. So, remember we are taking an intersection with g. So, out B 1 intersection g can never be bigger than B itself. So, this can be safely replaced by g, and that is the maximum that it can take. So, g union g can be nothing but just g. This is the maximum that can happen. So, we are whatever you want, if this had been bigger than g, then g union g prime would have been something bigger, but out B 1 intersection g can never be bigger than g, and when you take out something from that set g, it cannot be bigger than g either. So, this maximum that can happen here is g, and you get g union g equal to g. So, this is out B 2, and it will not change afterwards. What about the case when we initialize in B 2 to the universal set u? Out B 2 will be u minus k. So, this is as usual, and what about in B 2? So, we just took out B 2 as u minus k, okay, from the equation. What about in B 2, right? So, we have out B 1 intersection u minus k. So, this is out B 1 whatever is coming here, and this is out B 2. So, that is u minus k. So, the intersection of these two, and this is nothing but out B 1 minus k, because it is a very simple set theoretic identity. What about out B 2 2? This is again g union, take the same equations in B 2 minus k. So, out B 1 minus k, which is here minus k. So, that is out B 1 minus k, you cannot take out the same quantity twice. So, this is again a theoretic identity. Now, remember that this is a union here, okay, and this particular set is not necessarily a subset of G, it could be anything. So, because it is out of B 1, there may be lot of things inside which are generated and all that. So, whereas G is really the generation of B 2 itself, these two are not necessarily related. Okay, whereas here in the previous case there was intersection with G, that is why it was a subset of G, possibly a subset of G. So, this set could be different from G, there may be some overlap, but there may be some elements which are not necessarily in G. So, because of that this out B 2 is larger and more intuitive, but still correct. So, this is larger. So, it says whatever is generated within, and then whatever is coming here and what is killed, okay, remove what is killed. So, this is more intuitive, but at the same time still correct. So, the moral of the story is, if you initialize the in sets to u or the out sets to u minus k, we actually get a conservative solution which is still better than the other case when we initialize the in sets to phi. So, that is the reason why the initialization here was in b equal to u or out b equal to u minus e kill b, and not in b equal to phi as in the case of reaching definitions. So, this is actually a general rule. Whenever we have the confluence operator as union, we will have in b equal to phi and as the initialization. Whenever the confluence operator is intersection, we are going to have in b equal to u as the initialization. So, that is about available expression computation. So, now let us look at the third data flow analysis, which is a very important one, and we have already seen the result of this before, live variable analysis. So, we used live variable analysis information during register allocation. So, remember live intervals and live ranges, they are all derivatives of this live variable analysis. When do we say a variable is live? So, a variable is live at a point at the point P if the value of x at P could be used along the some path in the flow graph starting at P, otherwise x is dead at P. So, it is a very simple definition. So, for example, suppose we want to answer the question at this point, okay, is I live at this point. So, I is immediately assigned a value here. So, I is not live at this point. Whereas, if you take the question is u1 live, definitely u1 is not assigned any value, but u1 is used here along this path. Okay. So, is u2 live at this point? Definitely, because I can take this path to u2 and there is a usage of it. Okay. So, that is how we actually, if you look, let us take this point, okay, or even this point. I want to answer the question, is u1 live at this point? No matter which path you take, this way or you take this way, you will never reach this point, right. So, because of that, there is no usage of u1 after we leave this basic block. So, none of the points after this basic block B1 are live as far as the variable u1 is considered. Okay. So, this is how we compute define the liveness of a variable. There must be some usage without redefinition, that is the crux of the matter. This is a backward flow analysis problem, and the confluence operator is union. So, you can see that here the in function in the B set is computed as a function of the out B. So, in is a function of out, that is why this is a backward flow analysis problem, and the confluence operator here is u, and as a consequence of that, as I mentioned a few minutes ago, in B is set to 5 for all B for initialization purposes. In B is the set of variables live at the beginning of the basic block B, out B is the set of variables live just after the basic block B, this is as usual. Instead of gen and kill sets, gen set is the use set and kill set corresponds to def set. So, what is the def or kill of B? Def set is the set of variables definitely assigned values in the basic block B prior to any use of that variable in the basic block B. So, we want to define a variable without before using it in the same basic block. Use B is the other way, set of variables whose values may be used in the basic block B prior to any definition of the variable in the basic block B. So, let us look at the example to understand what this is. We want to, let us say, compute the use and def sets for this particular basic block B1. So, we have the variable m, the variable n and the variable u1 which are used in the basic block, but there are no definitions of the 3 variables before these usages. M is not defined before the usage here, n and u1 are also not defined before their usage here. Therefore, the use set of the basic block B1 will have m, n and u1. The 3 variables I, j and a are definitely defined in the basic block before any use of I, j and a. Therefore, they are put into the def set of the basic block B1. What about the basic block B2? If this is a little subtle, you must observe that the I here is the old value of I, and then there is a new assignment to I, and then onwards the new value of I reigns. Similarly, the old value of j is relevant at this point, and the new value becomes relevant after this j is used. So, as far as this I is concerned, it is used before a definition of the same I. As far as this j is concerned, it is used before a definition of j. So, both these are put into the use set of B 2. The def set, there are only two variables I and j which are assigned values here, but neither of them are defined before any use of that variable. See, I is used and then it is defined, j is used and then it is defined. Therefore, the def set of B 2 is phi, it is a null set. What about the basic block B 3? The use set is U 2 because U 2 is not defined, it is used before its definition, and the def set is A because A is defined before it is not even used in this basic block. And in the case of the basic block B 4, we have A and J in the use set because they are used before any definition. There is no definition of A and there is no definition of J either, but there is a definition of I and we have not used I. So, the def of B 4 is actually I. So, this is the definition of use and this is the def. The def corresponds to the kill set and use corresponds to the gen set. So, we will stop at this point and take up a detailed discussion of the data flow equations and the example next time. Thank you.